Theia, the colossal Mars-sized impactor, believed to have collided with the early Earth and ultimately given birth to our moon, has long remained one of the most mysterious players in the story of our solar system's formation. For decades, scientists have attempted to trace this ancient object's origins and determine whether it formed in the inner or outer regions of the early protoplanetary disk. Understanding where Theia came from is not just a matter of historical curiosity. It is central to decoding how Earth itself evolved from its primordial state into the habitable world we know today. New research suggests that Theia may have approached Earth from the direction of the Sun, a revelation that adds a crucial piece of clarity to a problem that has troubled astronomers and planetary scientists for years. Until now, conflicting theoretical models and real-world measurements have cast a thick cloud of uncertainty over the transition from proto-Earth into present-day Earth, as well as the true origin of the Moon. In particular, the lack of clear isotopic differences between terrestrial and lunar rocks has generated deep confusion. If the Moon was formed primarily from Theia, then its chemical fingerprints should differ significantly from those found on Earth. But they do not, at least not in the way scientists once expected. This puzzling similarity has forced researchers to consider a range of explanations, but none fully solved the mystery. The new findings, however, shed fresh light on how this monumental collision unfolded and why the Moon and Earth share such a striking isotopic resemblance. To understand the significance of this discovery, one must first look at how rocky planets form. In the early solar system, long before the Earth resembled anything more than a molten sphere, a protoplanetary disk of gas and dust swirled around the young sun. Within this vast rotating band, material gradually began to clump together through collisions, sticking due to electrostatic forces and eventually growing large enough for gravity to take over. These embryonic objects, known as planetesimals, collided repeatedly, merging into larger worlds. But this process was far from uniform. The chemical composition of the disk varied depending on distance from the Sun, meaning objects that formed closer to the star contained different raw materials compared to those that developed farther out. These variations included differences in isotopes, atoms of the same element with different numbers of neutrons, which act like cosmic signatures. Because isotopic ratios remain stable over enormous spans of time and decay in predictable ways, scientists can use them to identify where a planetary body might have originally formed. In other words, the chemistry of rocks can reveal their birthplace. In the case of Theia, researchers have long attempted to trace its isotopic fingerprints by comparing lunar rocks with samples from Earth. The idea is straightforward. If the Moon formed mostly from material displaced from Earth during the impact, then the isotopes of Earth and the Moon should match. But if the Moon formed largely from Theia, then its isotopes would differ. The challenge is that reality did not fit neatly into either scenario. Many isotopic systems, particularly those involving oxygen, titanium, chromium, and tungsten, appear nearly identical when measured in both lunar and terrestrial samples. This similarity is surprising because it is statistically unlikely that two separate planetary bodies, forming in different parts of the disk, would end up with matching isotopic compositions. That led scientists to consider several possibilities. One is that the Moon formed mostly from proto-Earth material, rather than Theia. Another is that the impact was so violent and energetic that it completely homogenized the material of both bodies, blending their chemistries into an indistinguishable mix. A third possibility is that Theia happened to form very close to Earth in a region of the disk with similar isotopic characteristics. But each of these explanations carries its own complications. Simulations of giant impacts show that complete homogenization is extremely difficult to achieve, and most models still predict that the Moon would inherit a large amount of Theia's material. Meanwhile, the idea that two independent objects formed with almost identical isotope ratios by chance is also difficult to reconcile with what is known about the variability within the early disk. This is where the new research provides a breakthrough. By analyzing iron isotopes in both Earth and lunar rocks, scientists propose that Theia may have approached Earth from the sunward direction, meaning it could have formed slightly closer to the Sun than the proto-Earth. This subtle difference in position could explain why its chemical makeup was so similar. The inner regions of the protoplanetary disk contained a more uniform mixture of materials due to higher temperatures and more frequent collisions among dust and early aggregates. Therefore, Theia forming just inward of Earth's orbit would have shared many of the same chemical building blocks. When the researchers studied iron-54 and iron-57 isotopes, specific versions of iron atoms, they found patterns suggesting that the Moon inherited much of its iron from an object that originated closer to the Sun rather than farther away. Because iron isotopes follow strict decay patterns and retain distinct signatures depending on their formation environment, they provide a reliable tool for tracing planetary histories. The new study suggests that the isotopic uniformity between Earth and the Moon does not require complete mixing or improbable coincidence. Instead, it reflects a shared neighborhood in the early disk. Theia may have been born slightly inward, migrated outward, and then collided with the proto-Earth roughly 100 million years after the solar system formed. This idea also aligns well with current models of planetary migration. In the early solar system, gravitational interactions between forming planets and the surrounding disk caused them to drift inwards or outwards over long timescales. These migrations frequently led to close encounters and collisions, especially among Mars-sized bodies. Theia could have formed in a zone where its isotopic composition was nearly indistinguishable from proto-Earth, but then slowly moved outward into a crossing orbit. Eventually, gravitational perturbations pushed the two bodies into a catastrophic collision. When they finally met, the impact was energetic enough to vaporize enormous amounts of material, launching debris into orbit that ultimately coalesced into the Moon. Most simulations indicate that this debris was made up of both Earth and Theia material, but the relative proportions have long remained difficult to measure. The new isotopic data suggests a scenario in which Theia's chemistry was already so similar to Earth's that mixing the two would naturally produce the matching isotopic signatures we observe today. The implications of this finding extend far beyond the origin of the Moon. If Theia formed slightly closer to the Sun, then it likely contained materials more commonly found in the inner solar system, such as refractory elements that condense at higher temperatures. This could have contributed to Earth's unusually rich composition of certain elements essential for habitability. Additionally, the manner in which Theia approached Earth could provide clues about the structure and dynamics of the early solar system. A sunward trajectory implies that proto-Earth and Theia shared orbital zones much earlier than previously believed, hinting at a more chaotic and dynamically active environment within the innermost regions of the disk. Understanding these movements helps refine models not only of Earth's history, but of how rocky planets form in other star systems as well. The new study also addresses a long-standing paradox in lunar science: the Moon's depletion in volatile elements. Lunar rocks are significantly poorer in volatile materials, such as water and certain gases, compared to Earth. This could result from the intense heat of the giant impact, which would have vaporized volatile compounds and allowed them to escape into space. But if the Moon inherited its material primarily from the proto-Earth, as some theories suggested, then it is harder to explain this depletion. The idea that Theia came from a sunward region helps resolve this inconsistency because the inner solar system was already hotter and richer in refractory materials. If Theia's raw ingredients were naturally low in volatiles, then its contribution to the Moon's composition becomes more consistent with observations. This connection reinforces the idea that the Moon's characteristics provide a fossil record of Theia's birthplace. While this new interpretation does not answer every question, it significantly narrows the possibilities and aligns the chemical evidence with dynamic models in a more coherent way. The Moon remains one of the most valuable scientific archives available to humanity. Unlike Earth, which constantly recycles its crust through plate tectonics and erosion, the lunar surface preserves ancient materials nearly unchanged over billions of years. By studying these samples in ever greater detail, scientists can peer deeper into the earliest chapters of Earth's formation and the violent processes that shaped the young solar system. The idea that Theia came from the direction of the Sun adds another layer of nuance to this story. It suggests that the building blocks of Earth may have been drawn from a more limited region of space than previously assumed, meaning the conditions for forming a habitable planet could be more dependent on local chemical environments than broad-scale disk variations. Future studies will likely build upon these findings by analyzing additional isotopic systems in both lunar and terrestrial samples. New missions to the Moon, such as those planned by NASA and other space agencies, may also collect fresh material from deeper or previously unexplored layers, helping to refine these measurements even further. As laboratory techniques continue to advance, scientists will gain an increasingly precise understanding of the chemical and isotopic relationships between Earth, the Moon, and any remnants that may still carry echoes of Theia's identity. With each new discovery, the story of our origins becomes clearer, transforming what was once a mysterious cosmic accident into a scientifically traceable chapter in the evolution of our solar system. The possibility that Theia originated from a sunward region not only clarifies its chemical similarities with Earth, but also strengthens our understanding of how delicate and interconnected the processes of planet formation truly are.